Okay, so you join me in the dungeon of Baker Towers today, where we're going to be doing another physics video, all to do with thermal conductivity. So here we go. Okay, so we're going to be doing a lesson on thermal conductivity, and we're going to be able to answer this question: what materials are best to make a frying pan from? So here is an experiment that I've done for you. We are literally going to watch ice melt. So let me start that off for you. And you can see that I've put two ice cubes, one ice cube in a metal pan and one in a plastic lunchbox. They're around about the same thickness and they're resting on a tabletop, so they're at the same temperature. There's nothing heating up either of them, but you can see the bottom one, so the bottom ice cube is kind of dancing around on like a layer of water, and you can see that water, so you can see that that bottom ice cube is melting whereas the top one isn't. So they were sat on the same thickness of material and the same temperature, but the one at the bottom that was on the metal melted quicker than the one that was on the top. So why is that? So what is the thing that makes stuff melt? Well, things melt because they get warmer and then they change state. But they've got to get some thermal energy somehow. So there's some reason that the bottom ice cube got more thermal energy than the one on the top, and that's actually because of conductivity. It's because of conduction. The ice on the bottom, the heat travelled through the metal a lot better than it travelled through the plastic, and so it went from the tabletop, which is at the same temperature for both of them, around about room temperature, around about 20 degrees, but because the ice is at 0 degrees, the heat transferred from the tabletop through to the metal, through to the ice, and then melted it, whereas the plastic didn't conduct the heat through that as well, so it stayed as an ice cube pretty much. Okay, so let's have a look at the transfer of heat. So conduction is the transfer of energy between particles in a solid. The energy moves from somewhere that's hot to somewhere that's cold. So if I put a flame or a source of heat underneath one side of a solid, then something like this would happen. The particles would start to vibrate more and the particles would collide into each other and transfer on some thermal energy. Now there's something a little bit wrong with this model here, is that the particles would already be moving slightly. So unless they were at minus 273 degrees, which is as cold as anything can get, then the particles would already be vibrating. So all that the heat would do is just make them vibrate more, and if they're vibrating more, then they would collide into the particles next to them more, and so transfer that heat energy on quicker. So what's conduction? How are the particles arranged in a solid, a liquid and a gas? So hopefully a little bit of revision for you. In a solid, particles are close together in a fixed rigid positions like that. In a liquid, the particles are still very close together, but they're allowed to flow freely between each other. And in a gas, the particles aren't touching and there are spaces in between them. So why doesn't conduction happen in liquids and gases? Well, from the model we've just seen, the particles were fixed together by bonds, and the heat moved from particle to particle because the particles vibrated and collided with the next particle along. In a liquid and a gas, the liquids can't do that because the liquid particles would move freely between each other and not necessarily collide into each other and pass the heat energy on. And in a gas, the particles may not even collide with each other to transfer on that heat energy. So what type of solids are the best conductors then? So solids are the best conductors, and liquids and gases can't conduct heat, but what kind of solids are the best conductors? So we will answer that question in a second, but let's have a look at this question first. If you want to just pause the video, you might just want to think about the answers to these two questions. These are kind of questions that you really need to understand conductivity. So have a think about it and then I'll go through the answer with you. So if you want to pause it there. Okay, so what is a conductor first of all? So a conductor is a solid material that allows heat to pass through it because vibrating particles collide with their neighbours and transfers kinetic energy to the next particle. Good examples are metals. So did you have a go at number 2? What is an insulator? If you did, then let's go through it now then. So an insulator is a bad conductor. It's a material that does not conduct because the particles are too far apart and do not transfer the kinetic energy because the particles either flow past each other or don't collide. Liquids and gases are good examples. The best insulators have very few particles, so a vacuum is the best insulator you can get. Right, so we've said that metals are the best type of conductors, so we're going to try and explain why. Conductivity describes how good a material is at conducting, basically. Conductivity depends on how closely packed the particles are in a solid. So here we've got two solids. We're heating them up with the same heat source, and the ones that are closely packed transfer the heat energy on quicker than the ones that are further apart. Okay, so this is all to do with the bonding. So we've said that solids particles are touching each other, and so it's all to do with how closely packed in, because of the bonding, these particles are. You can have different structures of solid, which means that some are slightly more spaced out, even though they're touching other particles, and some that are closer together. So conductivity also depends on how many free electrons a solid has, and this is all to do with metals. So if we heat up, there again you can see they're evenly spaced this time, so the particles between them are evenly spaced, and on the left we've got a metal, so something like copper, and you can see that the white circles are like the atoms, and then the blue circles are like the electrons. And on the right hand side we've got a non-metal, same space, particles, but there aren't any free electrons, so something like a ceramic, something like that. So we heat them up, and because the electrons also help to pass on the thermal energy, because they vibrate and they move around, and they also move around freely between the different particles in this sort of sea of electrons, then they collide with the particles and help to transfer that heat energy, whereas the one on the right, which hasn't got any free electrons, can't do that. So let's have another look at that. Okay, so we've got two things that make something have better conductivity: when particles are closer together, or when they've got more free electrons, they're better conductors. So what affects the rate of conductivity then? Well, there are four things that affect the rate of conductivity. So the temperature difference, we've said that heat will travel from somewhere that's hot to somewhere that's cold, and it will travel quicker if the temperature difference is larger. If the material has a better conductivity, then it will have a better rate of conductivity. So here we've got a pan which has got a metal and a wooden part, or maybe that's plastic, but they're two different materials. The metal pan part will have a high conductivity because it's made of metal, is the thing it's made of, and the plastic or the wooden handle has a low conductivity because it doesn't, because it's made of a different material which has a lower conductivity. The thickness of the material as well. It takes more time to conduct heat through thicker materials. So if things are thicker, then obviously it just takes longer for them to travel through. And also the surface area of the material. So more heat will travel through something with a larger surface area than one with a smaller surface area. So if we've got one brick, then some heat will transfer through that. If we've got lots and lots of bricks, then we can have more heat transferring through those bricks because there's just more surface area for the heat to transfer through. Okay, so this is the end of this lesson. This is what we should have been able to do. So you should be able to describe what conduction is. You should be able to describe what makes some materials better than others at conducting heat. And you should be able to describe what affects the rate of conductivity. Okay, so at the beginning of the lesson we asked what materials are best to make a frying pan from. Well, there are two parts to a frying pan, aren't there? There's the actual pan and there's the handle. You want to have the pan which has got a high conductivity, so that it will travel through, then let the heat travel through and cook your eggs or whatever else you're cooking on it. But if the whole thing was made of metal, then when you touched it, then that heat would conduct very easily to your hand. So you want something that's got a different material with a lower conductivity, which will allow the heat not to transfer through quite so well, so you don't burn yourself. Right, so that's the end of this one, all about thermal conductivity. I've been Mr. Baker, and I will see you next time. Thank you.